Hello everyone, welcome back to eSchool platform. Today we are going to present PUMATS solution June 2022 paper 2. So to begin with, we have the question 1 which is on quadratic equation involving roots alpha beta. So on the first question task says you are given a quadratic equation that's 3x squared minus 4x plus 2 equals 0, and the object of the question is to show that the expression is equals to 3. To show this expression equals to 3, so the very first task we have to know is the sum of roots given to us as negative b on a, and the product of roots we have c on a, as you can see on the slide. And again, from our expression where we multiplied alpha plus alpha on beta, beta plus beta on alpha, as a result we have alpha beta plus alpha plus 1. So combining and simplification, we have as 2 on 3 for the product of roots and 4 on 3 for the sum of roots. So simplifying, we have 3 as the key origin, which is the proof of the question task. In B, we show that or find the new quadratic equation given the new roots, which are 1 on alpha, 1 on beta. So we remind ourselves that the sum of new roots will be a beta on beta plus alpha over alpha beta, which should be 2 when replacing the initial values, and the product of new roots, when multiplying them, we have 3 on 2 as a result. So therefore our new quadratic equation, we have sum of new roots, product of new roots, generalize 2x squared minus 4x plus 3 equals to 0. Sub 2, we have polynomials. Under polynomials, we are objected to get the values of a and b. We remind ourselves that the polynomial is divisible by 2x minus 3, which is a factor, and leaves a remainder of 10 when divided by x minus 3. So using those two information, we can generate 2 equations simultaneously. So as the first equation you can see on the slide, we have 8a plus 4b equals to 20. That's using x minus 2, leaving the remainder of 10. And again, using 2x minus 3, which is a factor, we have a second equation, 6a plus 4b equals to 16. So therefore, simplifying and solving, we have a as 2, and then using equation 1, we have b as 1. In equation 2, we have functions and mapping. Here, the question is to show that f is injective. And then we have, let's say, subjective. Okay, that's subjective. Show that f is subjective. We remind ourselves that the domain is r restricting -1, and the codomain we have r restricted 1. So therefore, to show that it is surjective, we pass through the range of the function. In that case, we let y to be f of x, and then we look for the range of that function given to us as y plus 1 over y 1 minus y, to which the domain of the range gives us for all y in R, y should be different from 1. Therefore, f becomes surjective when the range is balanced by the codomain, that is mapping the entire codomain set. And the codomain set, which is given to us as R restricted -1, shows that the function is completely surjective. In B, we have composite function where we find f or f of x and find the domain of our composite function. So replacing our f, which is composite, that is computing f followed by f again, the definition of the composite function, generalize -1 on x as output. So therefore, it therefore exists if and only if x is different from 0. So our domain becomes, for all x in R, x should be different from 0. In sub 2, let's see, determine the parity of the function. Remind ourselves that the parity of the function is to determine whether the function is odd or even. So given our composite function f on f, we can be able to generalize that it will be even if f of minus x equals to f of x, and will be odd if f of negative x becomes negative f of x for all the input value from the domain of the composite function. So therefore we can see from our composite function we have -1 over x. So arranging the function, we can be able to see that the function is totally odd as the parity of that composite function. In sub 2, we have binomial expansion. Binomial expansion, to which we are asked to expand as a series in ascending power of x up to the term x squared. Here we rearrange the function first algebraically. We have as a result 1 minus x into 1 minus 2x to that power. Therefore, we can use the general expansion procedure, which says 1 plus ax to the power n, give us 1 plus anx to the term x squared. So therefore, using the expansion, there's the binomial expansion, 1 minus 2x to the power -1/3 generates 1 minus 2 on 3x plus 8x squared over 9. So multiplying again with the original 1 minus x, we can be able to generalize that our binomial expansion to the term x squared can give us 1 minus 5 on 3x plus 14 on 9x squared. In question 3, we have vectors. Vectors, here we have the question task A, which says we should find the equation of the line, that's the vector equation of the line in the form A plus TB. We remind ourselves that A is the line along AB. To have AB, we have OB minus OA. As a result, we have negative 4i minus 6j plus 10k. Therefore, the vector equation of the line along AB, which is the position vector plus the direction vector AB. So therefore, we can be able to generalize as I plus 5j minus 3k plus lambda into negative 4i minus 6j plus 10k. So equivalent to A plus TB, so we can find A and find B easily. In B, we get the position vector of M, where M, remind ourselves that the M is the midpoint to AB. So since it's in 3 dimensions, we're going to have as a result along the x-axis on 2, along the y we have on 2, and along the z on 2. So by summing them, we can have as midpoint negative I plus 2j plus 2k. In C, we get the Cartesian equation of the plane ABC. Remind ourselves that the Cartesian equation of the plane is the arrow dot n equals to A dot n, where n is the normal vector to the plane ABC, and A is the original position vector. So the normal vector is given as AB cos AC, that's the vector perpendicular to A, B, and C. So from there we can get the normal vector from the plane ABC, 22i plus 12j plus 16k. Therefore, our plane equation, which is in 3 dimensions, we have xi plus yj plus zk dotting along give us as a result 11x plus 6y plus 8z equals to 17 when simplifying. In D, we get the value of the constant A. We remind ourselves that here the vector equation of the line is parallel to the plane ABC. We remind ourselves that if the vector equation of the line is parallel to the plane ABC, then the direction vector of the line is perpendicular to the normal vector to the plane, as we can see. So as they are perpendicular, then the dot product should be 0. As you can see on the slide, that is the direction vector of the line should be perpendicular to the normal vector to the plane. So in that case, the dot product should be 0. So therefore, arranging our equation, extracting the normal vector to the plane and the direction vector on the line, we have as a result this for the line, and then for the plane we have this extraction. So dotting the two vectors, we can have as value a to be -5. In question 4, we have trigonometry. Trigonometry, where we have as a task to show that f of theta is equivalent to cos theta plus sin theta. Here we use basic identities of trigonometry, our original equation, where we can decompose tan theta as sin theta on cos theta, and cot we have cos theta on sin theta. So rearranging our expression, we have as a result cos square theta over cos theta minus sin theta plus sin square theta over sin theta minus cos theta. Therefore, we can have the QID, which is the proof, recognizing that cos square theta minus sin square theta can be decomposed using the difference of two squares. Therefore, we can be able to cancel the one at the denominator. That is, we can recognize cos square theta as cos square, let me say a square minus b square to be a plus b into a minus b. Some of the term will cancel the denominator, generating cos theta plus sin theta. In B, we get r and lambda using the wave function. With the wave function, we can be able to have an equivalence, which is cos theta plus sin theta equals to r sin theta plus lambda. We use the identity of trigonometry, which is r cos lambda sin theta plus r sin lambda cos theta. So pairing the two equations, we can have two simultaneous equations to be solved, which will permit us to solve for lambda pi on 4, which is tan inverse of 1. And then squaring the two equations, we can be able to use the condition as r is greater than 0. We have r to be with 2 units. So therefore, our f of theta can then be composed as 2 sine theta plus pi on 4 as our wave function. In C, we get a general solution, f of theta equal to 1. So remind ourselves that our f of theta was solved previously, can be used therefore to get a general solution, the gen sol. So from there, we make sine inverse of 1 over root 2, give us pi on 4 as PV, the principal value. So our gen sol having here theta, based on sine theta we have here. So making theta the sub equal to formula, we can be able to have the general solution. In question 5, we have sequence and series, where we are told that the sum of the 6th term and the 8th term of an AP is 40, and the 7th term is 4 times the 2nd term. So the question task is find the first term and the common difference. A, which is the first term, and Z, which is the common difference. So using our two information, we can be able to have T6 plus T8. That's their sum, and then we establish a linear equation, as you can see. So solving, we have as equation 1, A plus 6D equals to 20. So using the second information, which says that the 7th term is 4 times the 2nd term. So we have this result. So simplifying give us a second equation, A plus 6D. So therefore solving for A and D, we can have A as 2 and D as 3 based on the two simultaneous equations. In B, we find the least number of terms required for the sum of the progression to exceed 1000. So that is, we get n, which is the least number of terms. So we remind ourselves that the sum of the first n terms, first of all, we have as n on 2, 2a plus n minus 1d. So greater than 1000, we then solve for n. So solving for n, we have this equation. So solving like a quadratic equation, we can have from the formula method negative b plus or minus the square root of b squared minus 4ac on 2. So therefore we can have two values of n generated. So the two values of n can therefore be studied as n is greater than 0. We can have the least possible number of terms, 25.65. Approximately we have 26 terms. In sub 2, differentiation. Differentiation C, we are given y equal to sin x ln x. So we can only get the derivative as a slope by using the product rule. We let u to be the first expression, then we have v to be the second expression. So our du dx, as you can see, equals x, and our dv dx using the property of the limit function 1 on x. Therefore, by the product rule, we can have a generalized equation sin x on x plus x ln x. Remind ourselves of the product rule, which says that dy on dx is u dv dx, let's say v prime, plus we have v u prime, where the u prime and u dx, dv dx for v prime. In D, we have parametric differentiation, where you have to get dy dx. So given the parametric curve x and y, that's depending on t. So in that case, our dy dx can be gotten from the chain rule, and the chain rule, which is dy dx, giving us dy on dt times dx on dt. So differentiating each individually, we can have dy on dt 1 plus 4t cubed, and dx on dt giving us 3t squared. So by the chain rule, we can be able to obtain our gradient slope 1 plus 4t cubed divided by 3t squared. In question 6, we have complex number. The first task, we are to solve for z and w, to which we were given two simultaneous equations to work with. So solving for z and w, we can use either the elimination method or the substitution method. So our preference, if you use the elimination method, we multiply equation 2 by 3 and we add with the first equation. We can have this simultaneous equation here. W into 1 plus 3i equals to negative 15 plus 5i. So conjugating the bottom and making w the subject of the formula, we can have w as 5i. So using the equation 1 and conjugating where necessary, giving us z as 3 minus 2i. In sub 2, binary relation, where we are asked to show that R is an equivalence relation, we remind ourselves that R is an equivalence relation if it is reflexive, as case 1, symmetric, and transitive. So on the first case, we prove that it is symmetric, reflexive. So for it to be reflexive, we remind ourselves that it will be reflexive if all the points picked in the set, which is the set of natural numbers, maps or relates themselves. So having our definition, we can have A, B as other pairs relating AB. So we can have as B on B equals to A on A. So as equivalence, we have that A on A balanced by B on B. So the two cancel themselves, so we have 1 equals to 1, which shows that R is completely reflexive. Case 2, we prove symmetric. For it to be symmetric, remind ourselves that if x relates y, then y relates x for all x, y pick from the set of natural numbers. So we use the other pairs, that's A relating B, A, B relating C, D. So by definition, that's natural definition. So cross multiplying, we can have DA equals to BC. So rearranging our equation, we can have B on D equals to A on C. Therefore, we can clearly see that CD relates AB as other pairs. Hence, it is completely symmetric. The last case, we prove transitive. For it to be transitive, we need to have a new element. Our new element here is Z. So if x relates y and y relates z, then x must relate z for all x, y, z pick in our set of natural numbers. So by the definition, as other pairs, we have AB relating CD as equation 1, and using the second hypothesis, CD relates EF, generate as equation number 2. So eliminating our unknown value, which is C, or we can make C the subject of the formula from equation 1, we have as DA B. So replacing equation 2, we have as expression FA equal to B. Therefore, we can clearly see that CD AB relates EF. Therefore, our R becomes transitive. Hence, R is an equivalence relation. Question 7, we have partial fraction. On partial fraction, we remind ourselves that we have 4 types that defines our partial fraction. So here, to partial frac, we have to use type 1 and third type, which is a type 1, which is linear, and the third type, which is non-linear, that is having a quadratic expression. So by definition, we have a on x plus bx plus c on x squared plus 9. So using our LCM, we can have as equation this, as you can see on the slide. So method of comparing, we can compare the coefficients. We have for the A, we have as 2, and B, we have as -1, C 0. The comparing coefficient, we have 1 equals to A plus C. So as you can see, solving and simplifying generates our input to -1 and 0 for A, B, and C. Thus, we can have our generalized partial frac expression x squared plus 18 over x into x squared plus 9 equal to 2 on x minus x over x squared plus 9. The second part is to integrate. So we use therefore our partial frac expression solved previously. Then now we use a basic integration tool where we can see that our integral is distributive over the negative. So as distributed over the negative, we can recognize the first part, the first term, as the next recognition, and we can also recognize the second expression where we can add an external factor of half here, and we have 2 here. So it becomes a recognition, so which is ln of our denominator. So having our expression and substituting the boundaries, we can have ln 4 with 13 and 5. Thus give us our QAD, the integral from 2 to 4 f of x dx give us ln 4 with 13 and 5. Question 8, we have indices to which we have 4x, 4 to the power x plus 2 to the power 2 plus x equal to 12, where we are objected to solve for x value. We remind ourselves that we can break down 4 to be of the same base, 2 to the power 2x. I will break down again here so that we can be able to substitute as a parameter t equals to 2 to the power x. Then now we can be able to have a complete quadratic equation. It's supposed to be t to the power 2, so solving for the unknown, we have t equals to -6 and t equal to 2. So remind ourselves that the t is 2 to the power x. So for the first input, we have no solution, as a ln can only take positive real values. So using the second t, which is 2, we have a solution x equal to 1. In sub 2, we have curve sketching. With curve sketching, remind ourselves that it defines completely a curve based on our differential equation, where now we are objected to solve for the unknown. That's question 8. Okay, question 8, that's sub 2. Sub 2 is under matrices. Sorry, matrices. Where there are matrices, it says that we should show that A equal to 2. So here, using our column matrix, we can extract the cofactor 3. We get the determinant of the matrix, we have as 45 here. So therefore, solving for this value, remember ourselves, the determinant was 45. So solving our equation, we can have as QID A equal to 2. Then finding the inverse of the matrix, we remind ourselves that it's 1 over the determinant times the adjugate of the matrix M. So here our adjugate is M cofactor Euler transpose. So using our cofactor transpose, we can have as adjugate negative 24, 20, 13, 6, 15, negative 5, 5, negative 5, 8, and negative 10. So replacing and simplifying, we can have completely as our M inverse this expression. In the second part, we have system of solving matrix equation where we have to get x, y, z. Since it is hence, we can use the solved inverse above, where now we can generate the matrix of the system of equation 2, 3, 5, 4, 1, 6, 1, 4, 0. Then solving for the unknown values x, y, z, we can be able to generate a solution, expanding and simplifying. X is 9, y is 9, and z is negative 3. Question 9, we have differential equation A, where we have to solve the DE. Remind ourselves it's a first order differential equation which is completely separable, and then we integrate by introducing the integral sign on both sides of the equation, as it is completely separable of other one. So we can have here and here as a result because a k constant, but since it is having the initial condition, so using the initial condition when x is 0 and y is negative 2, we can have k to be negative 1. So therefore our curve completely becomes x plus 2 over x minus 1. In B, we have curve sketching, where we have to sketch the curve showing clearly the points as it approaches near its asymptote. So to sketch the curve, we have to first of all pass through the domain of definition of the curve. The domain of definition of the curve says if it exists, since it is a rational function, its denominator should be different from 0. So therefore our domain exists for all x in R, x should be different from 1. 2, we get the intercept. So when x is 0, we have y equals to negative 2. So the generated point will be 0 and negative 2. And when y is 0, we have x equals to negative 2. So our incubated point generated will be negative 2, 0. We have the next turning point. Remind ourselves that the turning point exists at a gradient slope. So we first differentiate our curve using the quotient rule. So we have our dy dx as negative 3 over x minus 1 to the power 2. So therefore at Tp, dy dx equals 0. So therefore, equating and simplifying, you see that negative 3 is equal to 0, which is completely a tautology. So there's totally no Tp. Asymptotes. The asymptotes, we have two types, the vertical and the horizontal asymptote. With the vertical asymptote, which is studied at the denominator, x minus 1 equals to 0, give us the first asymptote x equals to 1. When simplifying, on the horizontal asymptote, which is at limit point, x goes to minus plus infinity. So solving for the highest degree of x, we have as result y equal to 1 as our HA asymptote. The second dot is the variation table. We remind ourselves the variation table is defined based on the domain set and the TP, if at all it exists. So our variation table, as you can see, we have 1 as our first point here, from minus infinity to plus infinity. We remind ourselves that here is from the domain. Since there's no TP, so our variation table is uniquely defined on our domain set. And again, we have f prime here, and we have f shows this the behavior of the curve as it approaches near its asymptote, and then now f prime is the science study. 1 here is the critical point on the curve since it vanished completely at 1. And studying the signs, if you taking an interval between -1 and infinity and replace in our f prime that we have, this is our f prime here, so the denominator is always positive because of the square. So because of this negative, we have the sign here to be negative. Next thing, taking a point here is supposed to be negative here. Taking a value between 1 to plus infinity, we also have our point negative since the function f prime is always positive at the denominator. So because of the -3, our input here will be negative. So that's for the box for f prime. For the f now, the minus infinity in f is 1, which is an HA asymptote. So because it is it's negative here, it's then decreasing from 1 to minus infinity, 1, which is the critical point. And then now, since it's also negative here, so it will then take from plus infinity to 1, since 1 is our HA asymptote. So this gives us completely our variation table for the curve. Next thing is the monotonicity. The monotonicity now, we should study at each point on the variation table, where now we have for x in between minus infinity and 1, we see f prime is less than 0, that's negative. So therefore f is decreasing on that interval. And then now for x in between 1 to plus infinity, we clearly see that f is negative. So therefore f is our f prime is negative, so our f is decreasing still on that interval. So the last thing is a sketch. We can see our graph here, where we can have our vertical asymptote at 1, which is the vertical, and our HA asymptote at y equal to 1. Then now this is our complete graph, y equal to f of x here. So we can see that the reading of our graph is based on the variation table. For minus infinity to 1, the graph is completely decreasing. So starting our graph, we can see from minus infinity to our 1, which is here, the graph take a decreasing slope from here. And then now from coming back from the variation table, for 1 to plus infinity is still decrease. So our graph here, then as it ends here, it will appear here and then decrease from 1 to plus infinity. In question 10, we have logics and mathematical proof, where we want to show that P implies Q is logically equivalent to negative P and negative Q. So remind ourselves that we need to build a complete table of 0 and 1, or true and false. So P, which is true, false, then our Q, which will be a Q here. We have true, we have false, we have again true here, have here false. So P implies Q. So it's true and true, that which is true. But a true statement cannot imply a false statement, so it's false here. And a true statement, this is true here, and then we have true. So having not Q, which is the opposite that's of Q, it is true here, so it becomes here false. False here we have true, and true we have false, and false here we have true. So we can build the logic P and not Q. And we clearly study the not Q and not P, which shows that it is actually logically equivalent. Sub 2. In sub 2 we have Newton-Raphson method of approximation. We remind ourselves that the first question is to show that f is monotonic increasing. F is monotonic increasing if f prime of L of x is above 0. From there, when differentiating our curve, we have completely greater than 0 for all x we take in R. So which clearly shows that f is completely monotone increasing. In B is to show the existence of roots. So in that case, to show that f has a root between 0 and 1, they must have the change in signs. We have negative and positive for the other one. So which clearly shows that f exists or having a root between 0 and 1 such that f of x is equal to 0, which gives us our QID. In B, we show a new approximation for the iteration of Newton-Raphson, where we have to get the second approximation. We remind ourselves that from Newton-Raphson method, we have xn plus 1 equals to xn minus f into xn. So having the initial estimate or having the first estimate at 0.5, which is our half here, so we can be able to find f of half, which is negative 1 over 4. We get the derivative of the curve, we have 6x squared plus 3. Replacing f prime of half, we have 9 over 2. So when n equals to 1, we can be able to get the second iteration to 2 dp, so we can have x2. So replacing in our curve, we have x2 equals to 0.5 minus 1.9 over 4.2. So therefore, our second approximation becomes 0.56. Thanks for watching. Don't forget to subscribe for a new upload. So see us in our next videos.